You're muted, Ren.
All right. Thank you very much, Mayar. And maybe Hancheng can connect. The rest of the session will be moderated by Professor Anji Liu. She's a new assistant professor in computer science working in robust machine learning. And she just became affiliated with Minds, I think a few weeks ago. So I apologize, I didn't have her on the slides earlier today, but welcome, Anji.
Thank you, Renee. Hancheng, okay, I see the slides. Cool. It's my great pleasure to introduce one of our own. Hancheng is a fourth-year PhD student in electrical and computer engineering at Johns Hopkins, advised by Professor Enrique Malada. His research interests include deep learning theory, reinforcement learning, and network dynamical systems. His work has been supported through the Minds Fellowship. Today, he's going to talk about the convergence and implicit bias of overparametrized linear networks. Hancheng, the floor is yours.
Thank you, Angie, for the kind introduction. Hello, everyone. It is a great pleasure for me to give this presentation in the winter school. And I'm very glad to talk about the convergence and implicit bias of overparametrized linear networks. This is a joint work with Salma Tamoum, Rene Vidal, and Enrique Machado. In deep learning, neural networks are typically overparametrized in the sense that there are much more parameters than training examples. In this case, the learning problem is highly underdetermined. So there are many possible solutions that fit the data perfectly. But in practice, variance or gradient descent often finds those solutions that happen to generalize well. This has motivated a lot of recent works trying to theoretically understand the nonlinear training dynamics of gradient-based methods. Prior works have suggested that in this overparametrized regime, using specific initialization may affect the convergence rate and leads to implicit acceleration. And other work have shown that certain initialization may bias our training algorithm towards some solution that generalize well, also known as the implicit bias or implicit regularization. This work studies very specific initialization, and we will see some of the examples later. But maybe we can ask a broader question. Are there general properties of initialization that benefit convergence and implicit bias? With this question in mind, we study the gradient flow dynamics on two-layer linear networks, and our work suggests that the answer in this setting should be an yes. In particular, our work provides general conditions on the initialization that guarantees exponential convergence for the flow and implicit bias to the minimal norm solution. And I will start with the convergence part. Existing analysis for convergence of two-layer linear networks requires strong assumptions on the initialization. Either the initialization has to be balanced or spectral. Balanced initialization requires the weights to be in some sense similar to each other across layers. And the spectral initialization requires us to carefully design the eigenspace of the weight matrices according to the SVD of the training data. People have looked at the non-spectral initialization, but only for the balanced case. In this case, the convergence relies on the notion of margin. The definition of the margin is related to the distance from the network model to the optimum. And the reason why we need the margin is mostly technical, and I will get to the details later. But the main point is that we cannot get rid of this balancedness assumption. But when we're trying to do that, prior work only studies the spectrum case. In our work, what we do is trying to generalize all previous findings to any non-spectral and imbalanced initialization. Specifically, what we do is to lower bound the convergence rate using the weight imbalance and the margin at initialization. Using this lower bounds, we can derive exponential convergence guarantee for the flow if the initialization has sufficient imbalance or sufficient margin. Before I present the the main results, let me briefly talk about the problem setup. We consider the linear regression problem with input data matrix capital X and output data matrix capital Y. We use two-layer linear networks UV transpose as our linear model. We define the squared L2 loss for the regression task. And 2 points is, I want to make 2 points is that our network is assumed to be overparametrized in the sense that there is no rank constraints on the linear model UV transpose. Then we study the gradient flow dynamics on the squared loss. Since this is a short talk, I won't be able to show the detailed result for the full problem. Instead, I want to illustrate our convergence analysis using simpler examples. With some additional assumptions on the data, we can rewrite the loss function for the regressions as a loss function for the matrix factorization problem. And I will present our results mostly for this case. But still, before I do that, let me try to start with the simplest case by replacing those matrices by scalars. In this scalar case, we are trying to approximate the target Y by the product of two scalars, U and V, and with the squared loss, and we can write down the gradient flow dynamics. The first thing we define is the imbalance of the weights. In this case, this is exactly the difference between U squared and V squared. And this imbalance term is time invariant. Such invariance gives us a lot of information on the training trajectories. When I plot the UV space on the right, and I try to initialize my products as a fixed W0, then different initial imbalance will give me different training trajectories. Let's say if I do the balanced initialization, I initialize the D exactly equal to 0. Then the training trajectory will be restricted to this blue dashed line. But if I can choose another imbalance, let's say D equal 3, then the training trajectory will be restricted to this red dashed curve. So later on, we will see this imbalance will be very helpful in our subsequent analysis. So now let me talk about the exponential convergence. I still write down the gradient flow dynamics here. The first thing I define is this instantaneous rate, which is defined to be the minus L dot over L. If we can find a constant lower bound on this instantaneous rate, then using Grunwald's inequality, I can show that the loss function converges to 0 exponentially. So the problem of convergence is reduced to finding a lower bound on the instantaneous rate. And under the gradient flow dynamics, we can explicitly write down the rate as 2 times U squared plus V squared. Using some algebraic relationship among the Y squared, imbalance, and products, I can rewrite the instantaneous rate as a function of the imbalance and the product. This expression is very interesting because we already said that the imbalance is time invariant and it is determined at initialization. So to get a lower bound on the rate, we only need a lower bound on the product squared. And this is where the margin term kicks in. Through a chain of inequalities, we can show that the absolute value of the product stays above the margin. The first inequality is simply the triangular inequality. The second inequality is because the absolute difference between the target Y and the products is non-increasing. I name the last terms as the margin at initialization. If this margin term is positive, then we can absolutely lower bounds the product squared by margin squared. And following those arguments, I finally get a constant lower bound on the instantaneous rate that only depends on the initialization. And that depends on the weighting, it depends on the weight imbalance and it depends on the margin. And this is exactly what I promised in the introduction slide. From this lower bounds, we can derive exponential convergence guarantees. And specifically in this case, if we're trying to plot the initializations in terms of their imbalance and products, Then sufficient imbalance guarantees exponential convergence. And in this case, the imbalance should be non-zero. And another region with sufficient margin could also lead to exponential convergence. And this region requires our initial product is somewhat close to the final target Y. Okay, now in this slide, I summarize what I have discussed for the scalar case on the left. And I will show you is what I can show you is that since doesn't change too much in the matrix case, is that those observations can be completely generalized when we're trying to replace those scalars by matrices. In the matrix case, we can define the matrix imbalance as a difference between U transpose U and V transpose V. And this matrix is still time invariant. And next thing we do is trying to find a lower bound on the instantaneous rate that using the three imbalance quantities and the products. And those imbalance quantities will be scalar functions of eigenvalues of the imbalance. Using this rate characterizations, we can derive exponential convergence guarantee when the initialization has either sufficient level of imbalance and sufficient margin. Let me talk a little bit about this imbalance quantities. When we look at this expressions for, when we look at the expression for the imbalance, it is a difference between two matrices. So this matrix will have positive eigenvalues and negative eigenvalues. Then for some particular imbalance, I can plot those eigenvalues, and then from those eigenvalues, we can define those imbalance quantities very easily. In particular, we define positive spectrum spread as the difference between the largest and the smallest positive eigenvalues, and we can define the negative spectrum spread similarly for the negative eigenvalues. And the last quantities I want to define is the level of imbalance, and it is the minimum gap between the positive and negative eigenvalues. And in all cases, we consider those quantities can be properly defined, and those are they are all non-negative. So recall that in the scalar case, we can explicitly write down the rate as a function of the weight imbalance and products and the product. But in the matrix case, since get a little bit slightly complicated, we can find a lower bounds using those imbalance quantities and some singular values of the product. When you look at the expressions, we roughly just replace the scalar imbalance by the level of imbalance, and we have some extra term that corresponds to the spectrum spread. And the precise result is shown below. And indeed, we can lower bound the instantaneous rate using imbalance quantities I introduced last slide and some singular values of the product. And you see that this lower bounds consists of two parts, and each part is of the form that I described above. With this lower bound on the instantaneous rate, we basically follow the similar argument in the scalar case. First, we know that the imbalance is time invariant, and with proper definition of the margin in this case, we can lower bound the squared singular value of the products by margin squared. So then in the end, we will get a lower bound on the rate that depends on the imbalance and the margin at initialization. And that bound will give us exponential convergence guarantee via sufficient level of imbalance or sufficient margin. Let me try to plot those conditions alongside the prior works. Here I plot all the non-spectral initializations that has been studied for this gradient flow. People have look at this balanced initialization where the imbalance matrix is exactly zero. That corresponds to the blue dashed line here. Prior work also studied the cases with sufficient margin, but strictly requires the initialization to be approximately balanced. So that is a gray region here. My collaborator Salma studied the case of homogeneous imbalance. In this case, the imbalance matrix is scalar multiple of identity. And in this case, there is closed form solution for this gradient flow. And when you from the rate from the closed form solution matches what I had showed you in the previous slides. And here is my conditions for exponential convergence, that is sufficient level of imbalance shown in blue, and the region of sufficient margin shown in orange. And the point is that our analysis mostly cover the entire UV space. My last slide for the convergence is for the full problem of linear regression. And for the matrix factorization, we have showed that we can lower bound the rate by imbalance and margin. And for the regressions, we have to account for the spectrum of the input data matrix. In particular, we will multiply our lower bounds by the least square singular value of x, and we need to scale down the margin by the top square singular value of x. In the last few 30 minutes, I will briefly talk about the implicit bias. For the implicit bias, we specifically ask the question, can we achieve both implicit bias and fast convergence? When we try to initialize network weights close to 0, we will obtain low rank solutions along the trajectory. But in this case, the convergence is slow. Other work has studied the kernel regime. The analysis works for general nonlinear networks. The convergence is fast, and we get minimum RKHS norm solution. But in this case, the kernel regime initialization requires us to randomly initialize the weights, and we have to make the network width sufficiently large. And in our work, we already have exponential convergence guarantees from the previous part, and we will provide additional conditions that requires some orthogonality among the weights. Combining those two conditions, we can get fast convergence to the minimal norm solution. And our conditions are not specific to the kernel regime, but they are general enough to include those kernel regime initialization. Let me first talk about the minimal norm solution. Suppose that the input data matrix capital X does not have full row rank, then there are infinitely many solutions to the underlying linear regression problem. And among those solutions, minimal norm solution is the one with the least Frobenius norm. As I said in the introduction, our conditions require some orthogonality among the weights. So to show that, we first need to decompose the first layer weights U into U1 and U2 using the SVD of capital X. The U1 is basically the projection of U onto the span of the data, and U2 is a projection onto the subspace that is orthogonal to the data. And then with some orthogonality among the weights, we get exact minimal norm solution. The precise statement is shown here, and we only require some orthogonality among the weights V and U2, and some orthogonality among the weights U1 and U2. Excuse me. If the orthogonal initialization is satisfied and the flow ever converges, then it has to converge to the exact minimal norm solution. Notice that this orthogonal initialization may not converge at all. For example, if zero initialization satisfies this, but 0 is a saddle point of the flow. But from the last part, we already have the exponential convergence from either the sufficient imbalance or sufficient margin. So I can combine, say, the convergence guarantee, sufficient level of imbalance, and orthogonality conditions. Combining those two conditions, I can get fast convergence to the exact minimal norm solution. And now when I look at the initialization in the kernel regime, what I can show is that those two conditions are approximately satisfied with high probability when I initialize in the kernel region. And with that, I can easily show that under the kernel region initialization, I can converge fast. We can get fast convergence to an approximate minimal norm solution. And again, I want to emphasize that our conditions are not specific to kernel region, but they are general enough to include the kernel region. So to conclude, we study the gradient flow dynamics on two-layer linear networks, and we provide general conditions that guarantees us the exponential convergence and implicit bias to the minimal norm solution. And for future works, we want to extend our convergence analysis to other type of losses, such as exponential loss for classification. And we want to generalize the analysis to deep linear networks with more layers. But ultimately, I hope that our analysis for linear networks could give some insights on understanding the general nonlinear networks. And that is all I have. Thank you for your attention, and I'm happy to take any questions.
Thanks, Hancheng, for the great talk. I think while others are coming up with questions, I have one question actually exactly about your future work. So in this work, you mainly focus on this more simpler linear networks. What are the challenges if you want to generalize to this like more complicated, or there's a lot more like nonlinear networks?
Yes, thank you. That's a great question. So the nonlinear, so I would imagine that convergence analysis could have can be maybe in its ultimate form could be generalized to the nonlinear networks. The reason is because the notion of imbalance still exists for nonlinear networks, and there are recent works that studies this imbalance matrix and how does those invariance properties still holds in the general nonlinear networks. So people already look at this invariance properties, and we see that this invariance property is already very powerful in understanding the dynamics in linear networks. If such invariance is preserved or partially preserved in general nonlinear networks, maybe we can use those type of invariance properties to understand the convergence, following the similar argument that I had previously. So maybe the first step would be understand more on this imbalance in the nonlinear networks, and second step would be connect those imbalance to the convergence.
Cool. Are there any questions in the audience? Another question maybe I have is about like how this theory, like how do you connect like this theory to the practice, right? So did you also like do like simulation and like whether those are like reflected or validated in any of the like for example experiments?
Yes, we did some initial numerical experiments, and what we see is that so here is the thing is that there are two factors that affect the convergence, right? You have the imbalance and maybe the product if you take back to the how do we look at the rate. And right now the experiment is more about maybe just looking at particular one factor, which is the imbalance. So maybe in some cases, in some experiments, we do just to make the products just very small so that we can see how those imbalance affect the convergence. And we see that this imbalance matrix really tells a lot more to the convergence of the linear networks than what I have showed in the slides. So maybe, yeah, I don't have the formal result right now, but I am still working on that to design more good examples, experiments to show how the imbalance, how good the imbalance is in terms of the convergence.
Got it. Cool.
Thank you.
Any other questions from the audience? I think if not, I think we can break for a little bit. Maybe we'll have 4 to 5 minutes before we can resume together to introduce the next speaker.